workshop goals are to discuss the state of the art and potential applications for AI/ML for APS-U First Experiments. Topics that we're going to talk about are real-time on-the-fly data processing, smart in situ and operando experiments, ultra-fast phenomenon dynamics, AI/ML assisted workflows, digital twins for electron and X-ray characterization, data infrastructure for synchrotron and nanoscale user facilities, and AI accelerators for fast training and inference. So we are having this over 2 days, the morning of today, April 19th, as well as tomorrow on Thursday, April 20th. So our first session today on autonomous experiments, we'll have talks from Sergey and Ilya from University of Tennessee at Knoxville and Oak Ridge National Laboratory, respectively. We'll take about a 20-minute break and then come back for a session on AI/ML for dynamics experiments, and there'll be 3 talks. And that session will be led by Subramanian. And then tomorrow we'll start up again at 9 a.m. with a quick recap. And our first session will be on AI/ML for diffraction experiments that will be chaired by Matthew. And then we'll have our another session afterwards on AI/ML for imaging and spectroscopy experiments chaired by Chengjin. So each speaker has a 30-minute time slot to give their talks. We ask that this be about 25 minutes of presentation, followed by about 5 minutes of Q&A. We will be pretty strict on time to keep everybody to that time slot. And we do ask that you hold your questions for the Q&A period after the talk is done so we can move quickly. With that, I'm going to ask our first speaker, Sergey, to share his slides and get started.
Fantastic. Thank you very much for the introduction. And it's a great pleasure to talk about some work that I've done with my colleagues in Oak Ridge and now continue at University of Tennessee, Knoxville. So all of you know me, so I've been at a sort of frequent guest at Argonne at the time when the travel was a thing, and hopefully it will resume in the near future. So as a general background, I spent 20 years at Oak Ridge, sort of going from Wigner Fellow to the corporate fellow. Then, as a lot of colleagues before me, I decided that it's time for me to join an academia. The only unusual element is that I spent a year at Amazon in the special project divisions, so roughly the Amazon equivalent of the Google X, to see how the technologies transform from the scientific ideas into the product. So that was kind of very interesting experience that adds to the capability to the position, the scientific R&D in the context of the things that add value. And interestingly, this time has already strongly affected the direction in which I think to take the research forward. So let me start with the motivation. So obviously we live in the materials world. And if we want to make better materials for energy self-driving cars, the displays, we need to improve the existing systems. So if we want to come up with the fundamentally new capabilities, we need to discover new materials, such as room temperature superconductors, new materials with a high mechanical stress, and so on. Very often we need to engineer materials. So if we talk about the solid state quantum computing or single atom catalysts, we actually need to make them. However, it's not enough to make things on the lab level. So we need to think not only about the functionality, but we also need to think about the manufacturability and cost. So these are the 3 parts that determine the applicability and usefulness of any specific material. Now, once it comes to the basic science, as all of us know, sort of whether you are in the university or national lab, and especially the user center, that the academic and industrial R&D are equally based on the instrumentation. So obviously, this type of pictures are great to show for folks who deal with the computer science and the machine learning. For all of you, this is everyday reality, so it's difficult for me to imagine anything more impressive than the synchrotron. But ultimately, the tools that we use, either for synthesis or characterization, they tend to generate data. It is natural for us to focus on the tools that generate a lot of data, such as electron microscopes or synchrotrons. However, practically, each scientific tool, whether it is a pipetting robot or the readout system, generates some amount of data. And the question becomes, what do we do with that? So one thing, that trend that has existed for at least last 20 years and probably more, is the trend to optimize the use of the tools in terms of efficiency of time use and putting the people with the right expertise in the right place and the right time. So one example of it is the user facilities, right? So there is an extra value in putting several electron microscopes side by side and having the qualified staff working with them and working with external users to explore their data. Another example, so for me as the proud ex-Amazonian, is the cloud computing. So in 2006, Amazon said that, look, you don't have to have the computers on premise, you can actually have an access to the data storage and the networking as the part of the cloud ecosystem. So that's obviously changed the computational world quite a lot, and it changed the way startups operate in this field. But the interesting part is that very often we talk about multiple tools of the same type connected to each other, or we talk about the multiple tools put together in one facility, but not necessarily interacting with each other. The question is, can we do better? And let me show you an example of the topic that is fairly close to my heart, which is the synthesis of the hybrid perovskites. So where do we start? We start with the reagents. So once we have them, we can produce the inks and use them to do the combinatorial synthesis of materials, and then use the photoluminescence to study their stability and properties. We can use the same reagents to grow the single crystals, and then we can study them using the classical physical measurements, or we can study them by the neutron scattering. Or we can use the same reagents to produce the films and measure the physical properties, take the mass spectrometry imaging, or perform the cathodoluminescence. So what it is an example of the workflow that is implemented in a fairly small lab. All of us are familiar with that. If you work on batteries, you deal with one type of workflows. If you work with the PLD growth, you deal with a different type of workflows. If you work in the chemical lab, this is the third part of the workflow. The key element of this workflow is that we learn and we plan it dynamically. So if I synthesize a specific material and I discover certain behavior during the combinatorial synthesis, I use this information to choose what films to synthesize. So there is some filter here. Based on the property of the films, I can decide what type of crystal to grow. And I know that this is much more time consuming, so I need to make a decision well. Same time of feedback comes from the imaging experiment. So ultimately, I'm doing the mass spectrometry measurements, or cathodoluminescent measurements, or SPM measurements, not just for fun, but with the idea to learn some information about the material and optimize either manufacturing part or perform the selection of the individual reagents. So basically, once we talk about the lab workflows, we deal with a characteristic stochastic optimization problem. And this is where machine learning theoretically can help. But in order for doing that, we actually need to have the right machine learning tools. And we also need to formulate the everyday discovery problem in terms that machine learning can actually approach. Why does it matter? So, okay, I'm showing you the example of the workflow in the lab. Well, because once the workflows are designed in academia, they're adopted by industry. And very often industry does not actually discover new workflow. It only optimizes their already existing workflows. So if you ever talk to people who work for Tesla or even to the extent that they actually can talk about what they work on, they're not using any advanced developments in the electrochemistry. They work with the technologies that were developed 25 years ago. The question becomes, can ML help us design better workflows? Because we need to do it when we have a flexibility to do so. Same problems appear in the context of scanning probe microscopy. So it's basically a toy model for more complex physical synthesis and characterization, but you can get the gist of the idea even in this case. Imagine that I run the microscope, I image some part of the sample, I try to find out what part of the sample is interesting, so I can zoom in and zoom out. After a while, I will select the region that I want to study in detail. And the question then I study it, and then after the experiment, I will try to analyze the data. Again, the same question arises. Can I have a machine learning agent that will do the experiment planning, allow for the human in the loop intervention, and produce the data that is explainable? So what would it take to make it happen? So the part which is obvious is, first and foremost, I need to have a hyperlanguage that allows my machine learning agent to emulate the activity of the human operator. And in case of microscopies, it is loading the sample, overview scanning, position the probe, initiate the spectrum, and so on and so forth. So that part is obvious. The second part is machine learning. So how do you explore the real space image to find the objects of interest? And here, the interesting thing is that once you think about how do you make machine learning that allows you to make a better microscope, you very quickly come to realization that these machine learning methods are going to be universal. For example, discovering something interesting in the image plane of the microscope is virtually the same problem as exploring the phase diagram of the hybrid perovskite using the pipetting robot, except that instead of imaging or spectroscopy, you actually select the composition to synthesize. Interestingly, it is almost the same problem as using the machine learning to help you do the theoretical investigation of the phase diagram of some Hamiltonian, except that in this case, you calculate some ground state or some physical properties somewhere within the parameter space. And the part which I'm particularly excited about is the use of the machine learning and microscopy to explore the combinatorial combinatorial spread libraries. So for example, if you have a sample that is ferroelectric bismuth ferrite on the one end and the non-ferroelectric samarium bismuth ferrite on the other end, this sample basically encodes all the physics of the morphotropic phase system in just one sample. Our colleagues in the like Ichiro Takeuchi knew how to make the samples for 25 years by now. The problem is that if we want to learn anything about the physics of the sample, we actually need to know where to take the measurements. So I can do the electron or scanning probe microscopy measurements here, here, and here, but each measurement comes with a budget. I cannot take electron microscopy measurements every 10 microns. It's just prohibitively expensive. So as I mentioned, interestingly, machine learning is potentially the set of methods that can allow us to solve this type of problems. The question becomes how difficult it is. So interesting thing is that ML is actually existed for a while, but the time of the exponential growth of ML is purely the matter of the last decade. So there was a lot of enthusiasm in areas from computer vision to medicine to autonomous systems. But the interesting thing is that the progress and the impact as applied to experimental physical sciences have been minimal so far. And this is a kind of beautiful analysis by Ben Blazek at Argonne, obviously, who analyzed the evolution of publications in material science, chemistry, physics, computer science that actually use ML. Notice that chemists and computer scientists did a lot of ML with some healthy linear growth, and then once the deep learning become an accepted thing, there is an exponential growth. In physics and material science, there was virtually zero publications prior to 2016. So my own work in ML and physics started in 2008 and 2010. At that time, it didn't even register. Now, of course, it has become a big thing. So the question is, why is it difficult to apply machine learning for solving of the real world problems? The answer is very simple, because it requires first and foremost domain expertise and domain specific goals. Second reason is that the domain sciences are causal and hypothesis driven. Machine learning is data driven. There are other reasons. For example, machine learning is not a method, it's a culture based on open code, open data, and infrastructure. And of course, Argonne Materials Data Facility is a great paradigm for how to do it right. But most importantly, science is an active process. You basically go into the unknown, you try to discover something new and understand what it is. Machine learning, by far and large, is a great method to analyze the data, but not to extrapolate, not to formulate hypotheses, And the question is, can we do it better? So can we incorporate some of the machine learning elements into the scientific discovery workflow, starting from microscopy? And here comes the interesting part, that if I want to use machine learning agent to run my microscope, I need to first and foremost understand why am I running the microscope in the first place? What is my reward function? Let me show you an example of using a very simple experiment when I use a microscope to measure hysteresis loops in ferroelectric material. But you can think about it in any other setting. You can use the optical data to choose the place for nanoindentation. You can think about using the electron microscope to find the place where you want to do the ILS measurement. You can think about using AFM data to choose the place for X-ray tachography. So what is your logic? So let's say in this case, in the beginning, I will try to take measurements in these locations. So these are in-plane domains. I don't expect anything interesting to happen here, but hopefully being a good experimentalist, I want to choose the regions where I can get my background performance of the tool. Secondly, I will probably explore these regions where you have the stripy domain patterns, because this is the places that occupy most of my sample. After that, I can say, hey, these regions with these domains look like outliers. Maybe something interesting will happen here. Some of my colleagues will say, no, I mean, it's a good place to study, but the reason why it's interesting is not because it's an outlier, but because here you expect a frustrated elastic state of the material. And then somebody else will say that, you know what, the really interesting place is the one when your ferroelectric domain wall is bent, because this is you expect where you expect new phenomena because of the flex electric coupling. So notice what this discussion means. It means that when I'm running even a simple microscopy experiment, my reward function, so what I'm interested in, changes continuously during the experiment. I start with the instrument calibration. I proceed to the characterization of the statistically significant part of the surface. And then I actually start to guide my experiment based on my hypothesis about what physics is interesting. If I want a machine learning agent to run the same experiment, I need to be able to convey the same type of reward functions, and I need to be able to tune them on the fly. So, is it doable? Well, let's start from the very beginning. So the simplest example of the experiment is the one where you know in advance what is that you're interested in. And in those cases, machine learning works great. So this is the example of the Ensemble network that works as a plugin for the scanning probe microscope. It reads the data streaming from the AFM detector, and it converts it into the real-time semantically segmented data. So you can say that this is just an edge filter. If you look carefully, not really, because you can see that there are two types of domain wall here, the ones which are ferroelastic ones, like this, and the ferroelectric one, which are much sharper. Notice that our neural network found the ferroelastic ones, but it ignored the ferroelectric ones. So in this case, if we know in advance what is necessary, we can run pretty interesting experiments. For example, we can image the domain structure, we can find all the domain walls, we can select the points for measurement of certain signal, like a hysteresis loop, and then we can see how this hysteresis loop varies along the ferroelectric domain. And you can see that some of the variability is obvious. So there is a difference between left and right side of the wall. Makes sense because the wall is tilted. There is some variability which is less clear where it came from. For example, this variability. We can say that this may be related with the depolarization field between the large in-plane domains. However, in this, and of course we can do it for other instruments. So this is the example of the same type of the ensemble walls running on the scanning transmission electron microscope. So you can take an image, and then the neural network transforms the image into the atomic coordinates. So the unique thing here is that it can do it on the fly while the operator changes the resolution or sampling. So that's actually a difficult part because you have to deal with the very strong out of distribution drift. And once you have this type of operation, then you can do all kind of interesting experiments, like you can use electron beam to kick out the sulfur atoms following certain line, and lo and behold, you generated the atomically defined defects. For reasons that I cannot imagine, my colleague Kevin Rocapriori have chosen to write the letter R. Maybe that's a real proof of concept. And of course, you can do more complex things. For example, you can stream the data from the instrument to the supercomputer. That's kind of the point where it stopped a little bit, because microscope can generate the data every 100 milliseconds. A neural network can analyze it in the same amount of time. However, if we pipe this data into the atomistic simulation, those take much longer. So now we said that, look, we can deliver the structural data to the HPC, but now it's up to theorists to figure out how to analyze it fast enough. But this is all enabled for the case where we know in advance what we want to study. What if we want to discover something new? So find some specific behaviors. So traditionally, this is done using the methods used such as Bayesian optimization based on the surrogate Gaussian process models. So in our experience, starting from several years ago, for any real problem related to imaging, Gaussian processes in their pure form are almost useless. They simply allow us to improve the sampling by a factor of 3, which is in a real scenario of the microscope is absolutely not enough. So why does it happen? It happens for two reasons. First of all, Gaussian processes rely on the kernel function, which is essentially discoverable correlation function. And secondly, in real experiment, we never run a black box experiment. We have access to some information channel, and then we try to make things, use it to do the discovery on more detailed information channel. It turns out that Gaussian processes can be naturally combined with the deep learning networks to produce what is called the deep kernel learning. And these techniques are super useful for building the structure property relationship. For example, we can use the single shot deep kernel learning in order to discover where on the sample we have the manifestation of the large hysteresis loop opening. So just as an example, this is the example of the deep kernel learning running on the AFM. So you can see the kind of interaction of multiple moving parts, the instrument, the LabVIEW, and the Python notebook. We can run them on the electron microscope. And this is probably the example of the physical discovery. So we look at the plate of the layered material. We tell our machine learning algorithm that we want to find the regions in the material that have the largest ratio of the edge plasmon to the bulk plasmon. And lo and behold, you can see how the microscope finds the regions where this ratio is maximized. So this is unusual because in this case, we come up with a fairly general physical criteria and we implemented it on the working microscope. So it's not a simulation, that's actually the data from the, streaming from the neuron. We can also run the same type of deep kernel learning experiments on the AFMs, and kind of returning to the proverbial PFM, we can ask the microscope to find the regions where there is a maximum on-field hysteresis loop area. And you can see that the microscope has discovered the regions along the ferroelectric wall. So here, this is the experimental point. So you can see that microscope kind of made a few guesses, and then it kind of zoomed in on the domain wall as the region where the interesting behaviors happen. And if we try to do it in the off-field domain wall, then now we discovered that these behaviors are maximized on a different domain wall. So that was very encouraging because basically we figure out how to use the machine learning to discover the regions with the anticipated interesting physics, based on some proxy data. Question is, can we incorporate the physics as the part of the discovery process? Again, here the classical Gaussian processes don't work particularly well because they don't have any physics in them. However, it is possible to take the Gaussian process and augment it by the structural model that becomes the mean function in the GP. And this model can represent in the form of the equation and the priors on the equation parameters, the physical knowledge that is available for the experimentalist. So for those of you who are familiar with the Gaussian process, this is how the prior distribution look like in the normal GP. So your mean function is 0, and this is just a correlation kernel. And this is how the prior predictive distribution look at the structured GP. In this case, your prior functions are functions which are consistent with the physics of the problem, and the priors on their parameters is something that represents the prior knowledge. Turns out that this approach works remarkably well. So there are multiple papers from Maxim Ziadin, of myself, and our collaborators where you can read about it. But the interesting thing is that this approach can be expanded even to the situation where we have more than one potential physical model. So this is something that we call a hypothesis learning, and this is how it works. So imagine that you have a measurement system, which can be either synthesis or film growth or the AFM measurement or characterization of the microelectrodes on the combinatorial library. In any case, the outcome is the measurement. We use this measurement to inform our structural GP model. We also have the list of physical hypotheses, meaning the models with some probabilities. That is our second part of the equation. And basically, the algorithm does two things. One, it updates the models and its parameters. So this is our learning part. And secondly, it selects the region in the parameter space where we want to perform the next measurement. So, and the reason and the way you select this region is how to do it in such a way as to learn fastest. So the assumption here is that if you have a right hypothesis, then you learn the truth in the smallest number of steps. So in order to deploy it, you need to be a domain scientist first and foremost. And this is the example where it works. So we studied the same toy model of the tip-induced polarization switching. We know that there are several competing hypotheses what can limit the switching performance. It can be either thermodynamically limited or limited by the pinning or limited by the charge injection. So these are our hypothesis space. This is the video of how this process works in real time. So you have the autonomous machine learning agent that tells the microscope what to do. So in the interest of time, let me just show you the process. So this is our parameter space, the time and the bias pulse magnitude. You can see that we explore it, and then our microscopes start to compare the different models and figures out that the model number 3, meaning the domain wall pinning, is actually the correct one. So why does it matter? It matters because we basically combine the autonomous physical instrument and hypothesis-driven science in the same package. We have 4 hypotheses, and our instrument in the fully autonomous fashion checks which of the hypotheses is the correct one. And of course, we did it for AFM, but the same approach can be applied for any other physical instrument, as long as you have hypotheses and as long as you have controls. So what's likely to be the future? So the reason why I have shown the rewards and the real-time operation is because I don't think it's fundamentally possible to set up the automated experiments in the fully autonomous fashion. So when we have experimental planning, it's essentially a stochastic optimization of few wheel reinforcement learning problem, where we have to inform it with the prior knowledge, but we also give the reward that determines the procession of the experiment. If you imagine autonomous microscope, it will operate very differently, whether you tell it to find the origins of electromechanical activity or dislocation activity in the same material. We expect that the ML agent is going to take the low-level fast decision. Human agent is going to make the high-level decisions, whether it is change of the tuning of the policies or adjustment of the reward function. That's not anything that any of us are familiar with, because typically it is the human that takes the low-level decision, but it is possible. So we have the prototype workflows which show how it can be done. We need to learn how to build this type of workflows for more heterogeneous analysis when we have multiple instruments strung together. That's more complicated because we need to learn the value of our specific measurement. So if I take the microstructural measurement with the optical microscope, what is the added value of the scanning probe or electron microscopy in terms of my understanding of the physics of this specific system? This is a really exciting area, but we always have to explain what's the value of these advanced tools that you have, what the value do they bring to the scientific world. Typically, it is very speculative. Well, we need to understand physics. Maybe we can put a little bit more definitive answer to this issue. So I think machine learning can actually allow us to do that. It's also the opportunity to run much more complex experiments. Imagine that we have the same combinatorial library, which is studied at several places at the same time. We use the nanodenter at the UT Knoxville and the focus X-ray in Argonne simultaneously to, in coordinated fashion, study structure-property relationship. So combination of cloud and the ML agents with the workflow planning is the way to get there. So what are the key challenges? So the key challenge is that we need to agree on the language that is required.
Sergey, I hate to interrupt, but if you could finish up in the next 30 seconds, we're
absolutely getting there. So I try to summarize these key challenges in terms of this these points, and you can read more about it on our paper of workflows on arXiv. And in kind of anticipating of Nicholas' intervention, that's exactly where I plan to stop. Thank you.
Wonderful. Thank you, Sergey. This is a wonderful talk. Do we have any questions for Sergey? If you'd like, you can certainly just unmute and ask, or you could raise your hand in Zoom. Okay. Well, I'm sure Sergey would be happy to answer some questions later during the break, but in the sake of time, let's move on to our next speaker. Thanks again, Sergey.
My pleasure.
Okay. Let's see. Are you there?
Yes, I'm here.
Ah, great. Please go ahead and share your screen, and I think just go ahead and get started. Thank you.
Right. Let's see. Full screen. All right. Can you see the full screen?
Yes, looks good.
All right, excellent. Well, it's a really interesting story that Sergey gave, and he helped me actually to introduce the whole topic. But what I wanted to start perhaps with, I don't know if this one is on the way, is with a publication which brings a community perspective on autonomous experimentation systems for material development. It's an interesting story which brought together quite a few folks working on automation of experiments in material characterization. We're sitting here around 2023. And what's quite revealing is that research speed is expected to accelerate by a factor of thousands. And they anticipate the tipping points where all this interconnected experiments could be from the local integration and get to the global integration, leading to the thousands of researchers being able to access and optimize the material synthesis and material characterization. It leaves quite a bit of interest to the nanoscience centers and user centers because they have proven to be a really nice model by which users could access the capabilities. So I think we will see a brighter future, or bright future, continuously good future for the nanoscience centers in general. Let's move to another slide. Aside from the autonomous continuous flow synthesis that indeed is exploding in the recent years, driven by pharmaceutical industries, where the large range of reactor design from electrochemical, photochemical, high pressure, temperature, you name it, with the active feedback loop allows companies to produce pharmaceutical structures of interest, to the flow synthesis enabling to design really unique polymeric material with block polymers and unique architecture that's coming. One of the biggest advantage of flow synthesis indeed is that you're stepping away from a batch processing, and from the lab to the scale of production, everything can be done literally within one scale while increasing the yield of products and efficiency of your production. So this broad range of materials become available and will further grow, bringing interesting questions. Where would you use them? One of the interesting applications, I believe, is to revive concepts of bionic materials, bionic multifunctional materials, back in 2010, we look at the potential application of carbon nanotubes for generation of artificial neural bundle, which seemed to be reasonably well done with a glass material as a matrix, isolating about 19,600 conducting channels within the glass fiber, which is only 0.5 millimeter thin in diameter, using scalable technology, but it's not really compatible with biology. So new biopolymers, nanomaterials, integration of additive manufacturing, including STEM, cell engineering, along with it, could really drive these applications further. So in terms of workflow, Sergey gave a really nice overview of workflow. What we'd like to do in our system is actually to eliminate hours of human interactions, which are sometimes useful, sometimes useless, especially if we talk about modeling data, plotting dot plots, and so on, and integrating analysis of modeling software while running experiments. It's not only saving time, but basically allows us to realize real-time feedback for optimization of experiments where not a human being, but machine will optimize the experiment for material characterization. So in our case, we consider environment as our probe to look at the functionality of materials. And the single functionality is model dependent, of course. Therefore, integration of multiple functionalities brings benefits of selecting the right model, but also opens up opportunity to reach rich and good quality large data sets where you can look at the electronic, ionic, dielectric properties of material, details about diffusion of certain environments within the film, or porous structure, or changes in viscoelastic properties of the solution itself, while looking at the changes in NNK indices of optical constants, looking at the vibrational spectroscopy, Raman, fluorescence, absorption, and so on, including terahertz accessibility to the vibrational modes. And indeed, everything depends on what environments you implement, whether it's liquid environments, whether it's a gas environment, vacuum environments. The benefits here that you can easily integrate 3D printable environmental cells if high vacuum is not required, or generates PET-based structures for the flow cells. In general, environments allows you to go and probe all these materials across broad frequency range. In our workflow, we start in a software with setting up particular instruments, which then can be potentially changed. And we're looking at the combination of electrical, optical, gravimetric, and viscoelastic properties while changing environmental condition over the system. This experimental workflow details interaction of all these continuously tested properties of materials. We setting up environments in the incremental steps, allowing us to take time to stabilize system and then do the measurements and also feed these results. All these measurements, whether it's EC, electrical impedance spectroscopy, optical spectroscopy, gravimetric spectroscopy, or DC-based electrical measurements of the films, come together to be fitted by regression models to realize the predictive models for the next step of experiments. We've done this multi-functional assessment of materials using the lab on a crystal, which is based on a quartz crystal microbalance, flat polished piece of quartz piezoelectric material with the 2 electrodes on both sides. And we show that this material, this structure could be used to look not only at multifunctionality, but also look through different scales to probe material response on the macro and nanoscale. And indeed, multi-dimensionality as well as the multifunctionality brings tremendous improvements in the predictive prediction of materials response. For instance, if we take only 5% of a total data set, for the multifunctional response, we can improve prediction factor by a factor of 13 here. So we're moving forward with this lab on a crystal concept. Again, I mentioned quartz crystal microbalance. In this particular case, we're moving with dissipation. So not only that we're testing the fundamental position of fundamental frequency, we're also looking at full width half max. In most instruments, what you're looking at is the shift in the peak position, which indicates load or unloading of frequency because of additional mass added by analyte to the film. And this change in the frequency is monitored in the commercial systems. Only a single frequency is monitored plus some overtones. And what's really peculiar here is that you can see that the penetration depth of different overtones is different. So fundamental overtone, which is through the whole film, and the higher overtones touch and probe interface of materials. So thus, within one experiment, you can probe both the full thickness of material as well as the particular range distance from the crystal itself. In most commercial systems, the QCM probes viscoelastic properties up to 17th overtone. We created a system allowing us to go up to 31st overtone, and it brings tremendously diverse information on the thickness based response for thin films. This is just a few examples of the how the frequency of overtones change as a function of environments. You can see delta F is a shift in the frequency, and delta D is dissipation. What's really interesting looking at the instrument design, commercial instrument design, we realized the high resolution that is possible to achieve in the commercial system is limited because the range of sampling frequencies or windows of sampling frequencies is limited as well. So rather than once the peak as a result of environment shifts off the sampling window, you basically lose this peak, as you can clearly see in this commercial QCMs. So rather than stating a strict window, we decided to implement dynamic sampling window, allowing us to actually look at a very broad dynamic response of environments. So this is an example of monitoring one of the peaks of a QCM, and you can see some of the additional peaks coming here, which are hard to describe right now, but you can track the position of peak during this in situ experiments. And based on a model that you can feed the shift in the peak position while changing environments, we can use one of the 5 potential models. One of them is Butterworth Van Dyke equivalent circuit model of the film response, and not only monitor delta F and delta D, changing the frequency and changing dissipation of peak, which basically describes the properties of the material, but also you can deconvolute this response into the elements of the circuit while you're doing this experiments. The environment, changing environment results not only in the broadening of peak shifts, but appearance of additional peaks or from the neighboring overtones that you have not seen before. So complete tracking of not a single peak, but entire spectrum of the QCM response seem to be really important to be able to distinguish between which peaks you actually are tracking, and to be able to bring real information on the to the researcher. This is an example of software which runs simultaneously DC experiments, electrical measurements on a film, while changing environments. It also runs AC experiments, and we're simultaneously running the QCM or viscoelastic probing. Stop it before it starts flashing. Viscoelastic and gravimetric measurements on the same film, while also measuring the optical response of the film. This is all possible because of the QCM crystal itself being transparent, so we can look at the transmittance or reflection. In this particular experiment, we've done reflectance of the surface of the flat electrons. So there are a lot of instruments connected to the system. The current experiments was run in atmosphere, but as you can see, simultaneously with the measurements of impedance, measurements of a QCM, we on the background fitting this data, and in the end of the experiment, which usually lasts over 10, 15 hours, the data fitted and the models are presented to the researcher. What's particularly interesting about the computer controlled design of experiment, rather than running the DOE matrix, we're letting the machine to identify, to go back to the slide, work on the identification and fitting all the material response. So the first experiment is run at low P or P0 condition concentration of analytes, and then we're measuring the higher, and then machine selects which in other condition can be fit. So as long as the model that is developed in situ can describe the response of material, the experimental control could skip one or two experimental conditions rather than creating complete experimental matrix. Here, the interesting aspect of this experiment was the reversible versus irreversible, or rather slow response of zinc oxide versus copper phthalocyanine to the environment. And you can see how the model that is looking at response of material as a function of changing environment operates, and how just in a few steps, the reversibility indeed shows the benefits compared to the non-reversible response, but it'll take a little bit more steps to learn the material response and to be able to model both reversible and irreversible response with the same approach. So in the very end, the fast flashing screen that you saw on the software screen generates a report where you see both environmental steps and combined electrical multi-harmonic QCM response, spectroscopic response, DC, optical response, and other electrical responses on the film, allowing you as a researcher to, once you come and have your morning cup of coffee, to look at your material functionality. But more importantly, on the back of all these standard materials, the AutoML is running multiple models to see all these parameters and fit all these parameters. Indeed, training time for all these different models is very different, and one has to be really careful about how long you'll run the system. But in general, you can see, for instance, for these films where the minimum error is given by optical response, it shows the highest offset for a particular set of environments we studied. You can, once you have results, I mean, you have a freedom in your hands to explore also correlational spectroscopy. Majority of the experiments we're running in the correlation. And here we're looking at the impedance and phase correlation as a function of environment. It's pretty interesting. Here, you can, with this big and high quality data set, you can select only the fraction of your experimental set, this line, and use it as a part of the model, and see if we can predict the rest of the response. As you can clearly see on this image, just picking up a slice of a spectroscopic data as a function of RH, you can predict pretty accurately response to the entire system. Of course, there are models describing, for instance, QCM response with a film or a liquid on the surface. And this is one of these Wien-Voigt equations, which allow you not only to look at the data, but also look at the predictive models even before you start experiments. So we're considering right now running preset modeling before we jumping into model experiments to identify best material compositions. So this is just an example of how you can use this equation to model a system. The multifunctional response setup that we designed and implemented has been probed to different or applied to different materials, and you can see some of the samples of proteins and polymers and small molecules, perovskites, nanotubes, MXenes, metal oxide. Everything seemed to be working really well, and the wealth of information coming to you is really encouraging. The system design that I described earlier is published recently in Applied Materials Interfaces last year. so that's the reference to the paper that published this particular story. That concludes to some extent my presentation, but what I wanted to show you, I chat with GPT about autonomous experiments, and I realized that somebody has really to train this incredible feature. Because of a lack of information, it wasn't able to provide substantially useful information on autonomous experiment and material testing. But it's really incredible that by pushing a couple of review papers on chat GPT in less than 15 minutes, it spit out pretty reasonable conclusions on autonomous autonomous testing of materials, suggesting that increased exploration of design space is something that we will see in the next foreseeable future, and we'll be looking at identification of new and unexpected material properties using this autonomous experiment. Thank you.
Wonderful. Thank you for the great talk. We have some time for questions. So if anyone would like to ask our speaker anything, please either raise your hand in Zoom or just feel free to unmute and ask. We have a quiet group this morning.
Right. Well, I should mention that this system is a part of a CNMS user center capability, and the system can be accessed through the user research program. Small piece of advertisement.
Is everything you've done open source, or do you need to ask permission first?
Everything is open source.
Oh, wonderful. Okay. Well, since we do have some time, I guess it would open up to questions for Sergey as well, if anyone has anything to ask. Okay, maybe people will think up some things during the break. So we can go ahead and move on to our break now.
I was
sure. Go ahead.
Sorry, I was just going to ask maybe both the speakers. I know you kind of mentioned some of the X-ray facilities, but any thoughts on where you would see the greatest opportunities at synchrotron X-ray sources? More specific thoughts?
I can as well start. So I think that one of the analysis can be exceptionally useful, both from the point of view of the synchrotron development and kind of answering the lawmaker answers, is to explore where the planned future development and the synchrotron capabilities is going to make an impact. So let me give an example. So there was as you probably know very well, the progress in the resolution in the fields such as electron microscopy has been relatively monotonic, right? But in many areas of science, the impact of electron microscopy changed rather discontinuously. For example, in the cryo-EM, the impact of cryo-EM until maybe last 10 years ago was almost zero. It was not the most hot area of electron microscopy. Once the resolution of the EM crossed certain barrier and the data from EM become useful for the point of view of discovery of the drug targets, that's a totally different situation. There are now the companies like AstraZeneca who actually invest money into the cryo-EM facilities. So synchrotrons, of course, are much more kind of heterogeneous in terms of what type of systems they can explore, but being able to say that, for example, the planned development in EM is going to open these forms of scientific exploration and allow to understand specific phenomena can make a big difference. Because ultimately, in science, what matters, it's like in business, what matters, who is your customer and how large is the market. But doing the measurements for the sake of measurement is one thing. If you have a roadmap that says with the following investment, we would be able to solve such and such problem as relevant for medicine, biology, quantum computing, and so on, can make a tangible difference.
So one thing I'd like to offer is actually a combination of functional and structural measurements, the holy grail of materials. So if we can combine the functionality or multifunctionality testing with the synchrotron structural testing and incorporate some of the elements of functionality testing on the beams, for instance, using dynamic environments, that will be a tremendous benefit. And placing this data as a part of the free database accessible to all.
Great, thank you.
Great. Any other questions for our speakers? All right. Well, if not, I think we should go ahead and move into our break. So we will resume at 10:30 a.m. for our next session on AI ML for dynamics experiments. So I'll put up a little reminder slide so that we know that we'll resume then. And so have a good break and see you back in a little bit. Thank you.
Thanks, Nicholas.